This video is all about specific or adaptive immunity. Adaptive immunity is the most modern form of immunity in terms of immunological and evolutionary terms. Specific and adaptive immunity allows us to recognize germs, form chemical weapons to destroy them within our bodies. These are called antibodies. And then it allows us to remember this substance through not a cognitive or neurological process, but immunological cells have a blueprint, a pattern that they'll compare to future germs so that in a way that they can remember a particular substance and then react to it in a faster and more efficient way. The benefit of this is, of course, in a good way, if I'm vaccinated against a disease or if I survive a childhood disease, if that disease comes through my community again, I'm going to be immune to it because of these memory cells. Now, the ability of our body to adapt to and have adaptive immunity is predicated on this, antigens, right? We have to have large surface molecules called antigens. They're very much the same as what we had talked about in the blood chapter, right? Your blood type is based on your antigen. Your tissue type, if you're talking about a patient being on a donor list, right? That has to do with these cell identity markers. And here's the deal. We have self-antigens, of course, on the surface of our blood cells and tissues, and these are used as markers to allow the adaptive immune response to differentiate self from non-self. If you think about it, if I have these killer cells and cells with powerful chemical weapons, the last thing I want is for them to attack my healthy tissue. That would defeat the purpose of trying to protect me from the infection. So the antigen we're going to see is used as an ID tag to pass the message from one cell to the next. We'll come back and talk about this in just a little bit. Here we see some of these antigens. Look at this. This is a macrophage or maybe a neutrophil that found this germ or a foreign protein and then ate it and broke it all apart, neutralizing the germ or neutralizing this foreign protein. But look what it did. It saved the ID tag. And then it's using a special molecule here to post it on the surface. Now this is interesting. This is an MHC class 1 marker, major histocompatibility complex class 1. This is what it will use if it's trying to show that this cell has been infected. So what if this is a virus and this cell is now infected with the virus? It wants to be destroyed. It doesn't want the virus to be spread. So it posts the foreign antigen on its surface, which stimulates this cell to be destroyed. Likewise, if it accidentally consumed a self-antigen, it will post it on an MHC class 1 so that it doesn't stimulate cell destruction, right? It's saying, look, this is just me, don't eat me, don't destroy me. So there, that helps us understand foreign antigens are bad and we want them to be destroyed. Self-antigens mark our own cells and we don't want them to be destroyed. Here's another example. A macrophage or neutrophil eats a germ or a foreign antigen and it wants to pass the message along. It destroys the germ. It saves the ID tag. It uses a different molecule to post it, an MHC class 2 molecule. This is a way of holding this out to say, look, I'm showing this to you. But this is not my antigen, so don't destroy me. Don't eat me. Use this as a template presenting the foreign antigen to the next cell in line is the key to moving down this pathway towards antibody production. And this is a really important step in our adaptive immunity. It's called co-stimulation. So here's the same cell with the same MHC class II molecule holding out the processed antigen. And in this case, it's sharing it with a special type of lymphocyte called a helper T cell. The helper T cell gets a copy of this processed antigen, and it's going to then pass the message along to other white blood cells, which will bring us closer to antigen antibody production. It's very interesting. Once the helper T cell gets this antigen, it will copy itself. It will clone itself and split into a couple of different forms. Another helper T cell, which can be stimulated to divide again, to amplify the effect of this one alarm, right? Other copies may then go on to pass the message on to the B cells, the next big group. We also produce memory T cells, by the way. Memory T cells are going to go to the lymph nodes. They are sensitized to the specific antigen. So if this is chickenpox and I got chickenpox, when I was sick with chickenpox, I developed memory T cells for chickenpox, who now reside in my lymph nodes. Memory cells go to the lymph nodes to wait for the next attack. And so imagine I was infected with chickenpox, I had chickenpox, I was sick, but I survived. Excuse me, a year. I'm fighting a respiratory tract infection right now. I apologize for the coughing. Say a year later, I have a patient with chickenpox. Am I likely to get it a second time? Nope, because I have immune or memory T cells, which will then recognize the germ, come out, and go to work right away. So I might be infected a second time, but I'm not going to get sick. Okay, where do these sensitized helper T cells go? Well, they take their antigen and they share it with the B cells. The B cells here are also coming in with their MHC class II receptor. If they have processed the antigen, they can pass the message this way. If the T cells got it first, they're going to pass the message this way. In either case, we need to get to this level if we want to fight off the infection. And here's why. B cells divide to become memory B cells, who will go to the lymph nodes to await a second attack, just like the memory T cells. And some of them will become plasma cells. These daughter B cells might be plasma cells. And plasma cells produce the chemical weapons called antibodies. Notice that the shape of the antibody is complementary to the shape of the antigen. This is very important. It allows for these antibodies to be extremely specific. They're super powerful and deadly chemical weapons. We don't want them to stick to everything or we'll kill ourselves. We don't want them to stick to our healthy cells or we could develop an autoimmune disease. We want the shape of this antibody to be so specific that it only fits on to the germ who had the foreign antigen in the beginning. So if we go way back here to where it started, right? Then this macrophage ate the germ and then posted the ID tag. We have now created antibodies which will come back and stick to any of the germs that we didn't eat. And this is such a critical point. To use sort of a military analogy, you can send troops into battle, but if you don't send them weapons, they're not going to win the war. In the same way, you can send lots of white blood cells to the site of an infection, but you cannot win the war without developing antibodies. takes. And so you have to get through this whole process. Macrophages or neutrophils eat the germ and then post the foreign antigen. They pass the message to the helper T cell. This is called antigen presentation or co-stimulation. That makes macrophages or neutrophils the antigen presenting cells, APCs. So to whom does the APC present the antigen? To the helper T cell. The helper T cell then splits and becomes memory T cells, more helper T cells. It also becomes killer T cells or cytotoxic T cells, by the way, who can then go on target the specific antigen. And like an assassin, they can seek out the specific germ that is causing the infection. Helper T cells then pass the message to B cells, who become memory B cells, which go to the lymph nodes to await for a second attack, and plasma cells, which go to work right away, producing antibodies. You can't get to the you can't successfully fight off an infection, excuse me, like I'm fighting right now, without antibodies. And it is the plasma cells that produce those. Wow, what a lot of material. Here, table 22.2 begins to give you good flashcard material. Don't spend too much time looking at this table. Use this table as a reference and cut the material apart into different flashcards. Make sure you can understand what B cells do, what plasma cells are, what the memory cells are and where they go and what they do. The killer Ts or cytotoxic Ts, the helper Ts, and then we had talked about these other ones really briefly, dendritic cells, natural killer cells, and these other specific leukocytes, which are a part of innate immunity. The one thing I want to mention about regulatory T cells is that they are the brakes. They are the wet towel when inflammation and when adaptive immunity starts to go a little haywire. The regulatory Ts come in to tamp it down. Typically, this occurs after the infection has peaked, and there are chemical signals to say, okay, we've done the bulk of the fighting. We can now start to tame these other ones down. We're sure learning a lot about the immune system every year, and regulatory T cell dysfunction has been linked to autoimmune disease. You could imagine how this would work if the B cells, T cells are too ramped up, that this could result in too much inflammation. It could have to do with mistaken identity, where healthy cells are mistaken for bad ones. And then we end up with a condition called autoimmunity, where our immune system is attacking healthy tissue. Think type 1 diabetes mellitus. Think rheumatoid arthritis, or lupus, or multiple sclerosis, just to name a few. These are examples of autoimmune diseases, and to one degree or another, it may have to do with regulatory T cell dysfunction. It's also interesting to me, as a quick aside, that really the front line of cancer therapy right now is all about these cells too. And immunologists and oncologists have been collaborating to figure out ways that we can sensitize our adaptive immunity to recognize cancer. So, for example, if a patient has a leukemia or a lymphoma, it could be possible to sensitize our T cells to that blood cancer and then inject those sensitized cells into their bone marrow, where they would go and fight the cancer. This is broadly referred to as immunotherapy within oncology. And man, it is really shaking things up. There are a lot of very exciting studies showing some very dangerous and fatal forms of cancer being all but cured through this immune therapy. Really exciting. Some excellent videos you can watch. on your own time. Just a few more slides moving forward. We want to see how these antibodies work. Remember, it's plasma cells which ultimately form these antibodies, and they have a very specific shape which allows them to bind to only the foreign antigen that they've been designed for. Antibodies are also known as immunoglobulins, Ig, and we can see there are actually 5 families of immunoglobulins based on their shape: IgG, IgM, IgA, IgE, and IgD. Each of these works in a slightly different way, and some of them cross membranes into the extracellular fluid or the cerebrospinal fluid. Some of them are found in our sweat and our tears or in breast milk. We can actually see their shapes right here. And we can see their relative abundance as a normal component or percentage within the plasma or serum. We can also see some specific locations: IgA, saliva, tears, mucous membranes, and found in the milk to provide immune protection to newborns. The amazing thing is these babies don't digest these antibodies, but instead they just absorb them where they go to work in their body. Really interesting. IgM, excuse me, is the antibody which activates complement along with IgG. This one crosses the placenta, and this one is the transfusion reaction, the agglutination antibody. So a couple of different details that I'd like you to know about these. Here's the last one. IgE is the major inflammatory antibody class, and I think E for emergency. So if you think of an allergic reaction that results in an emergency: bee sting allergy, shellfish allergy, egg or peanut allergy, right? Not like watery, itchy eye allergy, right? That's not going to kill you. That's an IgA-mediated allergy, and it can be uncomfortable. But it is the IgE-mediated allergic responses that result in anaphylaxis. And if you look here at the details, you can see why, right? A major reaction triggering a lot of IgE can trigger degranulation of our mast and basophils, causing huge and sudden inflammation. So think of someone whose face suddenly starts to swell up, or their throat begins to swell shut and they need their EpiPen, right? That's an IgE antibody pathway. You can see how it works. The antibodies, again, having just the right shape to fit to their antigen, creates what we call an antibody-antigen complex. And once those are hooked together, it triggers this cascade of complement, triggering inflammation, chemotaxis, that's the attraction of white blood cells, cell destruction, and then we had talked about the membrane attack complex as well, marking them for death. These are all related ideas after the antigen-antibody complex. Specifically, we're looking here at those which trigger complement, which on this table remind us are IgG and IgM primarily. Here we can see how the antibodies could trigger inflammation. If the antibody on the surface of the cell, sticking to this activated mast cell, then once the antigen binds to it, it triggers chemicals within the cell to begin to exocytose and trigger inflammation. Here we see that idea being marked for death. The antibody-antigen complex triggers the response of the macrophage. So the germ isn't shown here. We could imagine if this were attached to a germ, that's like a blinking red flag saying, hey, come destroy me, I'm the bad guy. Here's the cool thing about the memory cells, ladies and gentlemen. They allow a shorter response time in a secondary response. Here's what I mean. When I was a kid and I got chickenpox, it took me a couple of weeks to really get over it. And although I didn't know it at the time, my primary response to this germ was a moderate production of antibodies. It was enough for me to survive the reaction. But look what happened the next time. The next time I was exposed to chickenpox, the memory B cells and the memory T cells, they woke up. The memory B cells in particular formed more memory B cells so that I could have additional long-lasting immunological memory. But look at all the plasma cells. Holy cow, they start pumping out antibodies by the boatload. And so I have a faster and stronger secondary response. We would measure this with a blood test called a titer, by the way, right? An antibody titer is a way of seeing how much antibodies were produced. And in this specific case, I never got sick a second time. Although I was exposed to chickenpox, I never showed symptoms. And it's because my secondary response was so huge and so fast that the virus didn't have a chance to set up shop. Now this begs the question, why can I get the cold several times every year? Well, it's because some viruses and bacteria mutate at a faster rate, and they have a way of changing up their antigens, and so by sort of stay under the radar. So you might think about influenza with this idea. There's H1N1, there's H2N1, there's H5N1, there's H5N5, there's H5N7, there's H12N4, whatever. The point is, the H and the N just denote different antigens on the surface of this influenza virus. And so when scientists discover a new form of influenza, they almost universally see it has a new and unique form of antigen. And so just because I survived one form of influenza does not mean that I will be forever immune to influenza, because it could mutate and then I could come up with a different variant. Now the good news is we can begin to build vaccines incorporating many more of these different antigens, so we can have, at least theoretically, broad field antiviral vaccines that protect us against multiple forms of viruses. Here we see the T cell idea once again. Activation of a T cell is going to give us these killer T cells and memory T cells. Memory T cells go to the lymph nodes and wait. Cytotoxic T cells are like assassins, and they can seek out the target cell with antigen and destroy them. Okay, almost done. The last few things we need to learn about are the different ways that we can develop acquired immunity. Active immunity means that our body has developed the antibodies on our own, and then we are immune. Acquired adaptive immunity means I got it along the way, I reacted to this antigen, and now I am protected against it. Natural active immunity means that I got the virus the old-fashioned way, through my food or through my respiratory membranes, or somehow I was infected and my body went through all of the processes that we've learned about in this video, and I am now immune to it. Artificial active immunity are really vaccines, right? Immunizations, whereby the antigens are deliberately introduced to the body. Now, most of the time, of course, we don't actually want to get our patients sick, so most of the time they use a broken virus, or they just isolate the ID tag so that the vaccine is incapable of giving the patient the actual illness, and yet the body responds to that antigen in the same way, and so the kid is immune to the thing. So, for example, measles. I've never had measles, but my body knows what it looks like because I was vaccinated. I got the antigen, which my body responded to, and so now I'm immune to it. By the way, it's sort of interesting. My kid, because measles is a live attenuated virus, he did actually get measles. One of just a few kids in the United States. He wasn't seriously ill, but he's in the literature because he did actually get measles from his vaccine. Super rare, sometimes happens. So Jonas is both artificially and naturally actively immunized against measles. I'm not going to get it if it comes around. Passive immunity means it's transferred from one person or an animal to the patient. That might sound strange, but just stick with me here. Natural passive immunity is what happens during pregnancy or during breastfeeding, when antibodies from the mother are transferred to her child across the placenta or through the breast milk. Artificial passive immunity is something that we've invented through medicine, where we can harvest antibodies from a horse, for example, or maybe from donated plasma, and then isolate those antibodies so that if we have a very sick patient, we can just give them a dose of antibodies to try to fight off the infection. For example, with meningitis, we know that it might take a couple of weeks for the patient to develop their own active immunity. We also know that with a lot of cases of meningitis, patients die within the first 72 hours. And so that might be a case where the physicians would opt to just give them a dose of antibodies if we have isolated antibodies towards that meningitis or hepatitis. That antibody therapy, immunoglobulin therapy is what we often call it, is a form of artificial passive immunity. So you should work on this, make flashcards out of this material, make sure you can explain it to your partners. Here's an overview of all of the stuff that we've talked about with adaptive immunity, seeing how the proliferation of the cells works, where the memory cells come into play. I'm skipping over all these videos that you should watch and listen to, but I don't want to waste your time reading or walking through the video with you. Good work.